way like the surface is shaped and like how it's bent and curved. So that's like this analogy of the roller coaster, but for surfaces. So what you see here is like we now often encounter these kind of expressions where we have the shape operator, and it's given by some inner product with a different vector. So it's like that happens quite often that we now get something like that. So the idea is to give that new names so that we can study these objects a little bit better and independent. So that's the next definition. It's the first fundamental form. Is it's like its beta is like 1, just the Roman 1. It eats a point and then 2 tangent vectors at that point. And what we want to do is we just take the inner product of both of these vectors. So that's just like a short short way notation for the inner product. And the second fundamental form is a similar form where we say we take here and we take the inner product of the shape operator applied to the vector W for the same data. So both of these fundamental forms, both of them are each 2 vectors and gives you a number. And you can of course write the second fundamental form also in terms of the first one, which sometimes is empty. Honestly, there's not much value in the first fundamental form, at least for this course, because it's just the inner product of 2 vectors, which are linear tangent. So there's not much value here, but the important object is the second fundamental form, because it encodes the geometry in terms of the shape operator, and essentially it's like the same kind of information as the shape operator. And why I give the first fundamental form is because if I write down that this one is the second fundamental form, you obviously ask me what is the first fundamental form. So like the more important object is the second one. Maybe for now I recall it, but I don't want to give the proof now. Maybe at some point I will do that. We have the following lemma, namely that these maps from TPS cross TPS into R are symmetric. So that means that if you change the position of the vectors, you get the same value back. For the first fundamental form, that's clear, because obviously if you take the inner product of 2 vectors, it doesn't matter in which order. For the second fundamental form, it's a bit more work to prove that. one remark about the first fundamental form. First fundamental form is the restriction of the Euclidean inner product to TPS, and as such it measures the metric properties. We call the metric properties of the surface. Okay. So like how distances, like the distance of like 2 points, for example, is something that is encoded with the first fundamental form. For example, the length of the curve in curve C and S is given by the following formula, which is the integral over square root So in that way, it's kind of like an important property. And the second fundamental form measures the curvature of the surface. And how exactly that will be like part of mostly next lecture. And we already had that quite often, that if you have like a geometric object on our surface, the first question was like, can we represent it in a chart? Because like that was like, for example, what we did with vector fields and with differential forms. So every time you have something something like the first and the second fundamental form, which is like something intrinsic, like this, like on the surface, you want to calculate it. And in order to calculate it, you usually need to have local coordinates. So let's look at the chart representations of these two fundamental forms. So if these ones are free, is a chart, and it's usually I need to use coordinates here in R2, which are just x1 and x2 instead of maybe x and y, because then we have like 1 and 2 as like indices. And then the chart representation by definition is the following matrix, where we say we have to take the chart representation and you get like a function of x1 and x2. And what you do is you evaluate the first fundamental vector, fundamental form at some point. in certain directions, namely in the directions given by these items, and then, of course, by using the definition of the first fundamental form, we can write this as the inner product of these two vectors by definition. So that's a matrix 2 by 2 matrix whose entries are functions of depend on x1 and x2. So that's the chart representation of the first fundamental form, and of course we can do something similar with the chart representation of the second fundamental form. To get a function again, and we do exactly the same strategy here. We plug in the partial derivatives in the directions that we choose. So let's use the definition. By definition, it's like the inner product of the first vector that we plug in with the inner product by the shape operator, which is minus the tangent map of the normal derivative. And now we have to use, like, in the direction of the second. And the minus sign comes from the definition of the shape operator. Now, we know that these vectors here, they are actually, so we would like to calculate this expression now. So what we do know about these vectors is that this vector is orthogonal to the normal direction over x1 and x2. So this one is 0. So now we take the derivative, and in the direction we want, like, is the derivative in the xj direction, so that we get here this term in xj direction. So if you take now the partial derivative in the xj direction, what you end up with is the second derivative of 5 in xj and xy direction, x1, x1, x2, times the product with the normal direction. And now we get the second term, which is plus phi dxi x1, x2 times, and now here we get the normal changing map in the second derivative. So this one is the normal direction in d5 dxj direction. And this whole sum has to be 0, because we have 0 here. So we plug in this expression here, exactly the one that we got, also nicely with the minus sign. So what we end up with is that second fundamental form in a chart given by x1 and x2 can be calculated in terms of the second derivative. It gives you a vector, and then you take the inner product with the normal. So in order to understand the second fundamental form, you already see here that it's like something in a normal direction of the second second derivative of the chart. So that's a quite important formula because it allows you to calculate the second fundamental form once you know the chart of the surface. Okay. Let's have a look at some example. An example is again we look at the sphere. Say that radius 1 has the chart which is given by theta pi sine theta sine phi. So it gives you a nice chart. So in order to calculate the first fundamental form, we have to take the derivatives with respect to both of these coordinates, because we need like these two vectors. So you can do that quite easily, but you end up with cosine theta phi minus cosine sine phi minus sine theta, and similarly you can take the derivative in the phi direction to get minus sine theta sine phi sine theta cosine phi and 0. So the first fundamental form is a matrix where each of these indices will take like the inner product of this vector with itself. The first entry, which gives us 1. If you take the inner product of this vector with this vector, you get 0. So not 0, 0 here. And if you take the inner product of this vector with itself, you get sine squared of theta. So that's the first fundamental form, written as a matrix. And you see both of these elements are like really functions of the coordinates. And last time we have seen already that the shape operator of some point in b direction was just minus b over the radius, but the radius is 1 here, so it's just minus the vector. So that follows that the shape operator, the second fundamental form, is just minus the first fundamental form. So if you just look at the definition of, what was it? Like, it's already gone, right? Like the the second fundamental form was like taking the inner product of the first vector. So here it's like the second fundamental form can be calculated in terms of the first fundamental form by just plugging in the shape operator in the second slot. But the shape operator here is just minus W. So that's why you end up with exactly the second fundamental form is minus the first fundamental form. And you can also get that result by just using this formula here, where you calculate the second derivative of the charts, and then you take the inner product of the normal to get also exactly the same formula. But I will not do that. Okay, so that's a nice example where we can actually calculate the shape operator. Usually it's I want to discuss another example, namely where the surface looks a bit like this, where we have like a plane, and then the surface is given by some kind of function. Where the snap is a function of two variables, so we have x and y here. And then to each point we kind of associate another point, and then we look at the graph. And that defines us, at least locally, some surface. And we would like to calculate how the shape operator of such a surface looks like. You can see that similarly to our study of the Taylor expansion of the curve, where we also did like the Taylor expansion of the curve. And what we found is that the Taylor expansion of the curve was determined by the curvature and the torsion, at least like to some order. So like similar here, we can like think of like, we would like to say like that the curvature of the surface, which would be the shape operator, would be kind of related to the Taylor expansion of the function that defines the surface. So that's like some motivation. So what we do is we consider the surface given by the graph of a smooth function say which is defined in some open subset of R2. So that says we look at the following surface, which is x, y, and z, where x and y are elements of U, and z is given by the graph. X and y is here. Here we have some open subset, and that one gives us the z direction. So that's our surface that we look at. And suppose that f of 0, 0 equals to 0. It's just like that. Essentially, that we have a 0 point here that we intersect the function there, and we say that we also would like to have the gradient of the function at 0 should also vanish. And the first observation is that this requirement that we have 0 there is equivalent of saying that the tangent space at 0 is this axis which is given by c equals to 0. So this one is equivalent to the tangent space at 0. Our surface is given by V1, V2, and V3 equals to that the tangent space there is 0 is this form. So let's have a look at how to prove this inequality, this equality. So how do you discover the tangent space? We would need to have some curve in the surface. Say it starts at the origin and as at the origin we have some vector v1, v2, v3. Because we require that the curve is an S, so we can write c of t as before as like a curve of x of t, y of t, and z of t. Because we require that c is a curve in S, follows that the z component can be recovered by the function as follows. So if you now take the derivative of this expression with respect to t at 0, what you end up with is that the c component at 0, which would be v3, and here we get that it's df in the x direction times at the point 0 times v1 plus df in the y direction at 0 in the v2 direction. So that means this requirement that dx and dy vanishes at 0 gives us that v3 has to be 0. Using that df. So that's intermediate calculation that allows us to identify the changing vector at some point at the origin. We can say like and you can calculate, essentially do the same calculation, but not at just like at 0, but at some arbitrary point, and you get an expression for the tangent space at some arbitrary point. And what you end up with then is that's your homework actually. Homework is to show that the following normal vector field expression defines a unit normal vector set. The calculation is very similar to here, and then you just show that this one is indeed normal. Okay, so we have our normal vector field if we accept that formula. So now we would like to calculate the shape operator. So shape operator at 0, say, in the direction of W is minus the change in space at 0 of the normal. So the normal depends, of course, on x prime and c. So these ones are functions of x and y. So we have to calculate the direction of omega 1, omega 0, because this one is changing, so there's no third component. So what you have to do is you take the derivative of these expressions that you have here in the x directions and in the y directions. So what you end up with after some calculation is that we have certain directions. So that's again vector field. So we have the x here. That's the x component, and then we have so that's, yeah, that gets a bit of a messy calculation, but after some cancellation, you see that you get a relatively nice formula. So to really show the steps, like in here, that's like as I said, like it's homework. And so we get now this expression. So what we now do in order to calculate the second fundamental form, we have to take the inner product with like some other vector. What we end up with following that we have just the inner product now of the tension W. So we take this expression, and what we end up with is it's 2, 0, V1, W1 plus issue F X Y and V1 omega 2 plus omega 1 plus where V1 is V1 omega W1. So you get this formula that follows just by taking the inner product there. And then we arrive at this formula. So that means you immediately see that the second fundamental form, which encodes the curvature, completely encodes also the second Taylor expansion. So we have here the Taylor expansion of f in the x direction in 2 more times. Here we have the mixed terms in x and y, and here we have them in y squared. So the second fundamental form is equivalent to knowing the Taylor expansion of the function. So that's the big upshot. Short is the second fundamental form encodes second order Taylor expansion. Function f. So really, it encodes like how f changes in every possible direction. So that's nice. And for the last remaining minutes, I would like to discuss how the second fundamental form is related to the frame. So we have, first of all, if you have E1 the frame adapted to S, then we can form the coefficients Ej by just plugging in E1 or like the frames. For the first fundamental form, that's kind of boring because E1 and I and Ej were orthogonal. So in this case, we just end up with delta Ij, which means 1 and 0 if I equals to j, and I not equal to j, we get 0. So for the first fundamental form, that's kind of boring. But like it's more interesting for the second fundamental form, where we do the same thing, where we plug in the frames at that point in the second form. And the proposition says that that we have the following expression, which we get is omega I3 can obtain as the sum over all j's from 1 to 3, 1 to 2, over these coefficients theta where theta j are the dual frame of EI. So that was the ones that we discussed last time, and these ones are the connection forms. So just give me like still 1 minute and I give you the proof because because it's really one line. So the proof is that we start with that omega 1 here in here, Pi. This one is the same thing as minus, but the symmetry is omega 3i here Pi, which was the same thing as minus tangent of E3 in P in this direction of here. So that's here. Now the free element was like the same thing as the tangent. So what we end up here is the normal direction of the n. So this one we get is the shape operator at P in the direction of V. So that's the formula that we also already had. So this means now if you take the inner product with Ej, you get these components. So it's Wi3 of V equals to Ei inner product the shape operator in V, because that's an orthonormal frame. So if you take the inner product of this expression here with Ei, what you end up with is exactly these coefficients in front. So what we get here is that the second fundamental form equals to, by definition, to Ei in the Ej direction. And yeah, so if you just do that, what you end up with that it's omega I3 in the Ej direction, which is just like exactly the statement. If you evaluate this side on a vector, we get essentially the dual. So that's yeah. So that's yeah, like nice formulas. So this one is like also important as an intermediate formula because it says like that we get like the fundamental, the matrix of representation in terms of the fundamental operators in these orthonormal frames. So it's a nice formula, and yeah, this formula in itself is also good because it tells you the connection frames, how they relate to this fundamental form. So these are like two ways to represent it. It's like either you can see these fundamental forms now as like the matrix representations of omega, as like a expansion of these one forms with respect to the dual, where there needs to be some coefficients. And like similarly, you can also see that as like the matrix representation of the shape operator. So I'm sorry that I took a little bit longer. Yeah, so that's for today. Next time we will talk about like the connection of these second fundamental form and curvature. So we really would like to extract a number and say like that the curvature of the sphere is like say -1 or 1. So really like get some numbers out of these shape operators. So that's going to be next time. Yeah, there was like someone asked me like how that connection forms is related to electromagnetism, and I promised to do that in the homework, but it turns out that like I need a little bit more time to like prepare you like with the material. So we do that actually not this homework, but the next one. I will talk a little bit about how these connection forms are related to electromagnetism. So don't worry if it's like doesn't pop up in the homework. We will discuss that at some point. Okay, then see you next week, and again, sorry for taking a bit longer.